the radionuclide. One of them is natural radioactivity, and other is radionuclide that we produce in the artificially. The main concept that we are facing with them in the physics of nuclear medicine is decay law, is activity, and also the half-life time. As far as you remember, I say, okay, as far as you remember, I said imaging when we have, okay, imaging when we have, please don't interrupt the class after starting the class. Okay, I said that imagine that we have, for example, 1 million cesium element with radioactivity, and I say, please pay attention that all of them cannot decay in an instance, and decay of this element will occur exponentially. So in each time, it is important to know the number of nuclear with radioactivity. And I say the number of nuclear with radioactivity in each time that's shown with n capital N equal the number of nuclear with radioactivity at time 0 multiply exponential of minus lambda t. And the other concept that I want to accept your classmates. Okay, the other concept that I wanna learn to you is about the activity. Then activity is the rate of disintegration of radioactive nuclei. And it equal lambda multiply n, or in each time we can say that activity in each time equal activity at 0 time multiply exponential of minus lambda t. And after that we reach to the other nuclear physics concept, that is half-life time. And based on this, I say that half-life time is the time that we need to reach the half of the activity, or half of number of nuclear with radioactivity. And I say, as the half-life time name implies, the half-life time is the time that taken for the activity or number of radionuclei to fall to half of its original value. After that, I say, besides physical half-life time, we have another half-life time, that is biological half-life time. In fact, when the radionuclide uptake into body, various biological processes such as respiration, urination, and detection are done to remove drug from the body. And the time taken for biological process to remove half of original active material from the body is called biological half-life time. And to consider the effect of both biological and physical concepts simultaneously, effective half-life time according to law equation is emerged. As you see, effective half-life time is less than physical and biological half-life time. After that, I propose to you some example, and I solve them. Then in the end of this class, I try to solve the question in slide 30 if we have enough time. Okay. After that, I speak about the main particle that emitted through emission of radionuclide, and that main of them are including alpha, beta, and gamma irradiation. At first, I start with the strongest particle, that is alpha particle. As far as you remember, in alpha emission, the number of the atomic number and the mass number of daughter are less 2 and 4 units less than modern nucleate respectively. As you can see here, the number of atomic number is 2 units less than the atomic number of modern radionuclide, and the number of mass atomic number in daughter radionuclide is 4 units less than modern radionuclide. And as you can see, alpha particle has 2 charge and has 4 mass of proton or neutron. So we can conclude that alpha particle has the highest charge and has the highest mass. And the other particle I speak about it is beta particle. A story about it is different with the story of alpha particle. As far as you remember, I said when the number of neutron is over than proton, a neutron decay into a proton alongside this reaction, and electron is created to maintain the charge conservation. And this electron with negative charge named beta particle, and as you see in this equation, when neutron converted to proton, an electron particle is produced. In addition, in this equation, as far as you remember, we have another particle that named antineutrino, that antineutrino produced to conserve the energy. I said in the last session that in each nuclear reaction we have 3 conservation. One of them is a conservation of charge, other is conservation of mass, and the last is conservation of energy. It is important to know that in each radionuclide process we have these three rules: conservation of charge, conservation of mass, and conservation of energy. And antineutrino in this equation produced to conserve the energy between the 2 sides of the equation. And the next particle that I explain it is positron. As far as you remember, positron or positive beta is emitted from elements which have a high proton compared to neutron due to decay of proton to neutron, and we can conclude when the proton converted to a neutron, a positively charged electron called positron is created. Again, here we have neutrino to maintain energy conservation. And the last is gamma ray, which is not particle, and as far as you remember, gamma ray is an electromagnetic radiation that are emitted from the radionuclide following beta or alpha emission, and also it is created when the daughter nuclei are left in excited or semi-stable state. As far as you remember, I say that gamma radiation can be occur in 2 situations. One of them is above the immediately after the main decay, when the radionuclide in the unstable state directly decay to a stable state with emission of alpha particle alongside gamma radiation. And also, gamma radiation can be produced when daughter radionuclides are left in metastable state. In metastable state, the only emission is gamma radiation. As far as you remember, I say gamma radiation can be occur in 2 situations, in 2 reactions in radionuclide process. And the last reaction that I mentioned to it, that sometimes occur in the radionuclide reaction, is electron capture. As you remember, I say when the number of proton is over than neutron, we have positive beta or positron emission, but when the differences between energy level of mother and daughter is lower than 1 to 0 mega electron volt, decay of mother radionuclide cannot accompanied by positron emission, and instead of it, we have electron capture. Same as positron emitter in electron capture. The atomic number is left unchanged, and the mass number is left unchanged, and the atomic number is reduced by 1. In fact, in this reaction, as far as you remember, an electron from inner layer captured into nuclear and combined with proton, and the production of them converted to a neutron. Due to losing an electron from inner layer, subsequently an electron from the upper layer will move to fill the space left by the electron in the inner layer. And in this process, we can also have an X-ray emission. Perhaps ask from you in which nuclear reaction we can have X-ray reaction, and you should say that in electron capture reaction we can have besides positron, besides particle emission, we can have also X-ray radiation, because in this process, because in electron capture the arrangement of electron orbital is different, and in this situation, with emission of X-ray reaction, we can return to the original state of electron arrangement. Okay. After that, I speak about the penetration rate of different particle into tissue into target, and again I started with alpha particle. As far as you remember, I said due to high mass and high charge of alpha particle react. It can have a very small penetration rate, and we can conclude that penetration rate of this particle is very low, or on the other word, it has the porous ability to penetrate matter. Again, I say that the lowest penetration rate or smallest pore is belong to alpha particle because it has high charge and high mass, or it is better to say it has the smallest pore. Perhaps ask from you which particle has the lowest penetration rate. That you say it is alpha particle due to this particle has the highest mass and highest charge. When alpha particle interact with tissue, it will be observed by a few micrometer of skin. So we are facing with external when we are facing with external resource alpha particle. It is not very dangerous for us, and it is important to know that alpha particle has a highest energy that deposits all of them in target, so it is very dangerous when with the internal source that emit alpha particle. It is important to know when we are facing with the external source that emit alpha particle, it is not very dangerous, but when we are facing with the internal source that emits alpha particle is very dangerous. We can conclude a source which is ingested will be very dangerous because the density of the internal ionization is very high. But when we are facing with the external source that emit alpha particle, due to absorption of alpha particle into your skin and because they don't enter to your body. It is not very dangerous. But when you ingest the source that emits alpha particle, this particle directly can damage your cell. Okay. After that, I speak about the beta particle penetration. For beta particles, due to having a wide range of penetration and because of their irregular paths, their depths in tissue cannot be accurately defined. But we can conclude the penetration rate of beta particle is very low, is very higher than the alpha particle. After that, we are facing with a gamma ray. That, as far as you remember, I say gamma ray is not a particle, so has no mass and no charge, and its interaction with target is completely different. As far as you remember, I think you learned this concept in radiology chapter that you have with Dr. Khoshbi. As far as you remember, the most important of gamma ray interaction with tissue are including photoelectron and Compton, and for gamma ray we don't have a defined penetration rate. But we have a very, very important concept about the gamma ray, and it is attenuation of gamma rays in tissue is proportional to the inverse square law. This equation is very, very important, and try to memorize it. And the last particle I said about it is neutron, and it's not very important because in the environment commonly we are not facing with this particle. After that, I speak about the different method that we can produce radioisotope. That I say, and as far as you remember in the first slide, I say we have two types of the radionuclide. One of them is natural radionuclide, and the other is artificial radionuclide. Due to very long half-lifetime of the natural radionuclide, we cannot use them as radionuclide, and so we should approach I said artificial radionuclide can be produced through reactor and through cyclotron, and in reactor we have different reactions that help us to produce radionuclide. Generally, for production artificial radionuclide, we should bombard the stable nuclear with charged or uncharged particle. In reactor, it is very important, and try to memorize it. In reactor, we use uncharged particle to bombard the stable state. Commonly is neutron. As far as you remember, we have different type of reaction in nuclear reactor. That one of them is fission reactor. That in this reaction, nuclear in this reaction, neutron bombard the high mass stable nuclear that generally is uranium, and when uranium bombard high mass uranium bombard with neutron, it split to different fragment, different radionuclide fragment. And the main point about the fission reactor is related to the high chemical purity of radionuclide produced radioactive daughter. And the common radionuclide daughter that produced through this method is molybdenum and iodine. And this you can see in fission reactor we can produce molybdenum and iodine, and in fission process we can have radionuclide daughter with high chemical purity. It is very important in radionuclide that we wanna use them as a radio drug. Okay, I only in this as far as teach I learned this subject to you in the last session, and I try to overview all of them. Up to now, I didn't start the next session. Yes, but I try to speak slowly. Okay. Again, I say. Again, I say to produce. Again, I said to produce artificial radionuclide, we have different methods. One of them is reactor, and the other is cyclotron. And in reactor, we also have different reaction. That one of them is fission reaction. In fission reaction, we can produce radionuclides such as molybdenum and iodine, and in fission process, we can produce radionuclide with high chemical purity. This properties is very, very important. Okay. As I say, in fission we have a large number of useful isotope that can be used as radio drugs, such as iodine and molybdenum. Everybody, please attention that in nuclear medicine we have different type of the radionuclide. That main of them are iodine and molybdenum. And typically, these produced radionuclides through fission reactor are beta emitter that are proper for therapy, especially for cancer therapy. Again, I summarize that in fission reaction, we have three important properties. One of them is related to high chemical purity of daughter. Other is related to common radionuclide that produced through this method, that are molybdenum and iodine. And the last properties, the last important properties about the fission reaction is about that typically radionuclide produced through this method can emit a beta emitter that is very useful in therapy, especially in cancer therapy. The other reaction that occur in reactor is in an gamma reaction. Or neutron capture reaction. It happens with a nuclear irradiated with a neutron and capture neutron and emit a gamma ray. For example, 31 phosphide is irradiated with neutron and then emit gamma. As you can see, the atomic number of mother and produced daughter is same, and we can conclude the produced radioactive daughter in this reaction has not has not high chemical purity, because the atomic number of mother and daughter is same, and we can easily separate daughter from the mother, so we can conclude that the produced radioactive daughter has not high chemical purity in spite of fission. Other event that can be occur when nuclide capture neutron is proton emitter. These reactions are less common and require higher neutron energy than previous reaction. The proton is ejected from the nuclide as a result of the absorption of neutron. The main properties of production of radio drug by this way is purity of produced radio drug, same as fission. Because in this reaction, as you can see, this reaction change atomic number, so the produced can be chemically separated from the mother nucleus, and we have high chemical purity of radioactive daughter. The main example of this process is carbon 11 from nitrogen for use as a labeling tracer of organic molecule in biological and medical reaction. The main property that you should learn is related to high chemical purity that I highlighted them in this slide. The other is an alpha reaction that is not very important. Up to now, we can learn that in reactor we have two reactions that help us to produce radionuclide daughter with high chemical purity. One of them is fission reaction, and the other is an proton and an alpha reaction. Okay. The other method that I said we can use for production of radionuclide is cyclotron, and in the main differences that are between the cyclotron and reactor is related to particles that bombard the stable nucleus. In cyclotron, in spite of reactor, we use charged particle for bombarding the stable state and producing artificial radionuclide. The main important properties of radionuclide that produce through this method is related again to high chemical purity. Again, I highlight them. Same as fission and in a proton reaction that occur in reactor, in cyclotron produced radionuclide has a chemical purity. Perhaps ask from you in which reaction we can produce artificial radionuclide with high chemical purity. In cyclotron, in fission, and in an P reaction. Okay, do you understand this? Do you learn it? I'm waiting to getting your answer. Yes, thanks. And the last method that we can use to produce artificial radionuclide is generator. It is important to know in medical we should use radio drug with short half-life time. So we need on-site reactor or cyclotron, for example, nearby a hospital or or nuclear medicine center, and it is not possible. A generator system enables us to produce radionuclide with short half-life time without need for an on-site reactor or cyclotron near the hospital. For this aim, the interested radionuclide data should have a short half-life time, and mother radionuclide should have long half-life time. As far as you remember, I said the separation of the daughter from mother is generated called milking. The common radionuclide that produced in generator in technetium 1990M or technetium in metastable state. That is a very, very, very important radionuclide that we use in medical nuclear medicine imaging. And the main point about this radionuclide or about this method is related to the concept that I wrote in this slide. As far as you can see, radionuclide generators are devices that produce a useful short-life medical radionuclide. Perhaps ask from you in which method we can produce a very short-life medical radionuclide. We should say in generator. We can produce short-life medical radionuclide from the radioactive transformation of a non-medical live radionuclide, such that called parent. The main in the generator, molybdenum 1990 in radionuclide state. When returned to a stable state, can produce technetium 1990M. And the parent in generator is molybdenum 1990 in radionuclide state that produce in a fission reactor. The main point that you should consider in the generator is related to the time that we can reach to the highest amount of data. As far as you remember, in generator we have production and also in fact you can in each generator we can milking technetium 1990M for about 4 times. After that, the new generator should be replaced. As the parent molybdenum 1990 decayed, the concentration of daughter technetium 1990M increased in the current. As far as you remember, I said the best time to milking the technetium 1990M or to reach the highest amount of technetium 1990M is about 4 times of its half-life time. And due to the half-life time of technetium is about 6 hours, we can conclude after about 24 hours, we can reach to the highest amount of technetium that produced in the generator. Okay? All of I say are the topic that I spoke about them in the last sessions. And from this slide, I wanna start the next section. Can I continue? Can I continue? Do you hear me? Can I start the next session? Yes. Yes or not? Okay. We have the as up to now I speak about the main process that we can produce different type of the artificial radionuclide. We have the wide range of artificial radionuclide that some of them are suitable as radiodirect. The main properties which appropriate radionuclide as radiodrug should have the different properties that are including at first having high chemical purities, such as radionuclide are produced by fission process or in cyclotron or generator. The other properties that artificial radionuclide should have to use them as radioderived is related to pharmaceutical behavior. They should have pharmaceutical with a suitable behavior. They should distribute can distribute in the organ or metabolic pathway in an efficient way. And the other properties that they should have is that radionuclide must have suitable radiation characteristics. Should have the proper radiation emitted and half-life time. For example, for diagnosis aim, they should emit gamma and positron particle, and for therapeutical aim, they should emit beta particle. Okay, in the following, we wanna know the main properties that artificial radionuclide should be have that can be used as appropriate radiodrug. At first, I start with the biological behavior that they should have to choose them as an appropriate radiodrug. The other factor that we should consider in selection of radionuclide based on our target. The radio pharmaceutical should localize and concentrate in the organ which is required to image or treat. Therefore, it should have maximum effect against targeted organ as well as minimum side effect on other organ. For example, due to accumulation of iodine in thyroid, for imaging or therapy of thyroid, we use different type of the iodine. Again, I say when we want to choose an appropriate radionuclide, the first property that we should consider is related to the which organ or system we want to image or treat them. So we should consider that this the desired radionuclide should concentrate in the target and have a minimum side effect to the other target. For example, as I say, for thyroid, we should use iodine because iodine is completely concentrated in thyroid. And there are different methods that we can use to localize the radionuclide in the desired organ. There are including diffusion, ingested, blocking, and recently with applying the antibody. It is interestingly to know some of them are practical, effective in certain part of the body. For example, diffusion method used in the brain. A small particle in colloid form can be ingested by the liver, and the other can be chosen so that they block the capillary and like in the lung. So we can conclude based on the target we should use radionuclide. And recently, with applying the antibody, we can selectively target radionuclide to a specific organ, and antibody use of antibody cause a revolution in the medical, especially in nuclear medicine. We can conclude, or in the other words, I can say that with using antibody, we can selectively target the desired. We can target the desired organ without damaging the normal organ, or with sparing the normal organ. As far as you remember, the other properties in choosing the appropriate radionuclide as radiodrug we should consider is related to the radiation characteristic, to them radiation characteristic. Besides biological characteristic, appropriate radionuclide should have some specific radiation characteristics that are different for imaging and therapeutic aim. For example, for imaging, at first for imaging aim, we have no permission to use radiation source that absorbed by tissue. So only we can use X and gamma radiation with 100 electron volt to 500 kilo electron volt interval energy. In this range of energy, we have lower scattering problem, and also detector easily can detect them. And the other parameter in imaging should be considered is half-life time. When the biological half-life time is of similar period to that of the investigation and the radionuclide is exerted, a long half-life time radionuclide can be used. Again, I say when we wanna choose an appropriate radionuclide for imaging aim, at first we should consider that they emit only X and gamma radiation with a specific interval energy. The energy, their energy should be in 100 kilo electron volt up to 500 kilo electron volt, and the other parameter that we should consider is about their half-life time. And for therapy, commonly for therapy aim, we use external radiation, usually from X-ray, that name radiotherapy. But for some organ we can't use internal resource. For example, unseeded or liquid form of some radionuclide that used in treatment. Iodine 131 is taken orally in moderate dose and in much lower dose for treatment of thyroid cancer. Moreover, the other radionuclide that we can use for therapy is phosphorus 32 and yttrium 90. And there are other radionuclides that we can use in therapeutical aim. As far as you remember, in the first slide of this chapter, I say the main differences that are between the X-ray imaging and nuclear medicine is about the high contrast that we have in nuclear medicine. And I said that with nuclear medicine we can study the body functionally. The main use of, or the main application of nuclear medicine is study the thyroid in functionally mode. One of the common use of radioisotope tracer is a dynamic function study, and this study cannot be carried out by method of external irradiation. One of the organs which can be evaluated with this facility is thyroid. Iodine, as I say, iodine 131 is given to the patient orally, usually as a sodium iodine solution. It is absorbed from a gastrointestinal tracer in the bloodstream and collected by the thyroid, where it is used to produce hormone. With iodine 131, we can image and treat the thyroid. In the following, the amount of absorbed iodine as thyroid function can be estimated by contrast, which is measured with a scintillation counter and then compared with a standard or model neck containing the same amount of iodine 131. Therefore, the uptake ratio is proportional to contrast from patient thyroid that divided by contrast from model or standard. Usually, it is recorded over a 24 hours period. The main point of this slide is related that with thyroid we can also say that we can functionally study the thyroid. And the other organ that we can functionally study is lung. For lung imaging, we can use technetium 1990M that tagged with albumin, which is part of human blood plasma, can be conjugated in saline and labeling with technetium 1990M. This is then injected into the bloodstream, where it is trapped in the fine capillary of the lung. And the other organ that we can study is bone deposits. And also with nuclear medicine, we can study the measurement of body fluids. And also we have a lot of other applications that is organ study in nuclear medicine. It is important to say that from a slide from 43 up to end of this slide are presented only for increasing your knowledge, and they are not as in your exam. Okay. From 43 up to 51 are slides that presented only for increasing your knowledge, and they are not very important in your exam. Okay, this chapter is over, and I try to mention to the main point that I learned to you up to now. If you wanna, I can also memorize them in a summary, okay? Or if you want, we can finish the class. This session is over. Okay, slide 30. Okay. Yes, we have, I think we have 3 sections in the next weeks. that are related to sonography, physical ultrasonography. That is very, very important for you as physician. The next chapter is related to physics of ultrasonography. Let's see an example. I didn't. You mean? Do you have any exam in the next week? Do you have any exam with that's related to other? Okay, you wanna have an exam with me? Yes. I. Let me thinking about it, and Dr. Hoshmin and I decide to take you exam. We inform you. Okay. Let us to thinking with each other, talking with each other. Okay. And about the slide 30. In this slide, I solve an example. And in this slide, we calculate the total activity of uranium. Naturally, it is important to know naturally uranium contains 90% of uranium 238 with half-lifetime of 4 to 5 multiplied 10 to 9 years, and nearly only 0.7 percentage of uranium is related to uranium with atomic number of 235 with half-lifetime of 7 multiplied 10 to the 5 years. The main point of this example is related to that when we are countering, we are facing with the element that contain two sub-elements, for calculating the total activity. At first, we should calculate the activity of each sub-element. Okay. At first, we should calculate the activity of uranium with atomic number of 238, and also we should calculate the activity of uranium with 235. Okay. Up to now, you understand? And for activity only, it is important to use this this equation. This equation is very, very important for calculating of each activity. You should use this equation. That base of this equation, activity equal lambda multiply number, and lambda, for calculating lambda, we should use this equation. We should use two equations. Okay, one of them is A equal lambda multiply n, and lambda equal half-lifetime divided lambda equal 0.69 divided by T And in question, you can find half-life time of uranium 2038 and uranium 235. Okay. For each element, you should calculate A with this equation. Okay. Do you understand? Okay. Thanks a lot. If you haven't any question and problem, we can finish this session. Okay. Okay. Don't be tired and goodbye. See you next week and so long. Bye.